Okay, next we're going to do the electroneutrality principle, which does sound a little bit like you've moved back into geography for a second, and that this is going to be like the Swiss in World War II, but that's not quite what it's like. But the electroneutrality principle is the declaration, we're still sounding like geography, the declaration that the electrons in a molecule are distributed in such a way that the formal charges will be as close to zero as possible. The declaration that the electrons in a molecule are distributed in such a way that the formal charges will be as close to zero as possible. So you may have found before, and maybe you didn't notice, but if you like drew a wildly different structure than to what I drew, and maybe you were like, I'm not exactly sure why it's wrong. I see that it's different, but I'm not sure why it's wrong. This is usually the reason. This is why we have to put the certain atom in the center, or why we have to put the double bond over here and not over there in some cases. So the electroneutrality principle will especially start to govern where you put the double bond on larger molecules where there might be 2 or 3 places you could put it, but only one is right. So we're going to go forward with that. Boron-containing compounds are unusual. They usually only contain 3 bonds instead of the usual octet. So let's take a look at that. Let's take a look at 2 possible ways to draw BF3. Okay, BF3. So boron brings 3 valence electrons, and then each of the fluorines brings 7. So you have 21 plus 3, you have 24 electrons. 24 electrons. So you put the boron here, and then you have your 3 fluorines. And if you were following the rules, the old rules, you would have done something like this. That was with only the old rules. And it turns out that one's wrong. That one's wrong. And the electroneutrality principle helps us see why it's wrong. The correct way to bond this is like this. And you think, well, boron doesn't satisfy the octet rule, and that's true. This is the way with the electroneutrality principle. And I probably should have left more space between these. But let's do this one first over here. So fluorine number 1, first fluorine, would have brought 7 electrons, minus 6 for dots, minus 1 for lines, and get 0. The second fluorine, though, would have brought 7, had 4 dots and 2 lines, and have a positive 1 charge. The third fluorine, 7 minus 6 minus 1 equals 0. And in this case, the boron brought 3, but now has 0 dots, 4 lines, and has negative 1. Okay, so those are the formal charges on the first one. And you say, well, Ms. Sprague, on some of the ones we did on the last page, some of the formal charges were negative 1 or positive 1, and that's true, but this will never occur in a case where one of the atoms is much more electronegative than the other. It will never be the positive. Fluorine can never have a positive formal charge. Fluorine can never have a positive formal charge. And the higher and brighter the atom is, the closer to fluorine it is, the more likely it is to have a negative formal charge, and the less likely it is to have a positive formal charge. And so electroneutrality principle kind of guides us to this structure where all the F's have 7 minus 6 minus 1, which is 0, and the boron has 3 minus 0 minus 3, which is 0. So this one is a better structure than this one. Boron not obeying the octet rule. Okay, and then let's do SO2. Okay, this is the way we learned how to do things. We said S is going to be in the middle, right? We said that we would put the S in the middle because it's lower and lefter than the O. But what if instead we had decided to try to do this? Like, what if we didn't know that rule? That was just a guiding principle. Both of these would have resonance structures, but it would have ended up something along the lines of this. And this would have been isoelectronic. So imagine it was like that. Okay, let's do the formal charges on here. We'll call the first oxygen, that's the second oxygen. Okay, so the formal charge here, first oxygen has 6 valence electrons, minus 4 dots, minus 2 lines, or 0. The sulfur has 6 valence electrons, minus 2 dots, minus 3 lines, so plus 1. And the oxygen has 6, the second oxygen, I should say. The second oxygen has 6 minus 6 dots minus 1 line equals negative 1. Okay, so that's one possible choice. And then here's this other choice where we put sulfur out to the other side. So we'll say the sulfur then has 6 valence electrons minus 6 dots minus 1 line equals negative 1. The oxygen in the middle, so that's the first oxygen. The first oxygen has 6 minus 2 dots minus 3 lines, or plus 1. And the last oxygen, the second oxygen, has 6 minus 4 minus 2 equals 0. Okay, so which one's better? Which one's better? The more electronegative atom, the atom that is higher and brighter, closer to fluorine, higher, brighter, closer to fluorine, should have the negative charge. Higher, brighter, closer to fluorine should have the negative charge. If somebody's got to have the negative charge, it should be the one that's higher, brighter, and closer to fluorine. So that would be the oxygen. And so this structure over here on the left obeys the electroneutrality principle. On your homework that's associated with this, you're going to draw a bunch of structures the way you would have drawn them before you listen to this lesson. Just the normal following the octet. Okay, on your homework, you're going to draw your structures twice. The first one you're going to draw is that you've never heard this lesson and that you're trying to make the structure just obey the octet rule and get all the electrons down the way we would have before this lesson. Then they're going to have you redraw all the structures so as to minimize formal charge. Redraw the structures so as to minimize formal charge. So you'll have to count the formal charge on all of those original structures and then redraw them in a way to give there to be double bonds or whatnot to make it so that the formal charges are as close to 0 as possible. So good luck with that.